In this video, we're going to recap electric fields, talk about work, potential difference, and get into some important ideas around batteries and how circuits work. Just to briefly recap, if I take a plate and I fill it with positive charge, and over here I take a plate and I fill it with negative charge, there's an electric field in between, and we've learned that these field lines point straight across. Notice that the field lines all point in the same direction. That's uniform. And the field lines are all evenly spaced. The strength is uniform. At the edges, that starts to deviate, but we kind of ignore the edges when naming this. We call this a uniform electric field, because everywhere the E vector has the same strength and magnitude. Magnitude and direction. If I take a positive charge and I hold it right here, does it have potential energy? If I take a positive charge and hold it right here, does it have much potential energy? Positive charges are pulled in the direction of the field lines. They're attracted to negative and repelled from positive. So this positive charge has a long way that it can fall. It can fall all the way down to this negative plate. And just like a ball that has a long way to fall, has a lot of gravitational potential energy, this positive charge, when it's crammed close to these other positives inside of the plate, that positive charge has a lot of potential energy. And until it falls and reaches this location, it'll still have some potential energy, and the energy will be all kind of run out when it reaches the negative plate. So if the charge moves in this direction with the field lines, the charge moves with the field lines, then it travels from the positive plate toward the negative plate. It loses potential energy because it's kind of just falling freely. Falls freely, just like as if it were a ball traveling toward the ground. And what about the work? The work done by gravity, not gravity, the work done by the electric field because after all, whenever there's a force applied over a distance like this, we have work. Work is the force, magnitude of the force, so this is absolute valued here, times the distance, times the cosine of the angle between force and distance. But wait a second, the angle is 0. Whenever the charge goes in the same direction as the field, these two arrows will be in the exact same direction. There's 0 degrees separating them. And cosine of 0, we know, is 1, positive 1. So whenever you move with the field, the work done by the electric field is positive. Conversely, we could set up some rules. If you take your charge, and here it is, it's getting pulled to the right, but you flick this thing, right? You give it a flick with your finger. How do I draw a finger flicking? You flick it with your thumb? I don't know. You push it briefly the other way. What happens? We can cause it to move against the field. So we can make this thing move toward the positive plate. And when it does, it's going to slow down, right? And eventually it's going to stop and turn back around and fall this way again. But for the time being, when we just look at this motion, it's going against the field. Q moves against the field lines. I'll just put, against field lines. And what do we notice? Well, now the angle between the distance and the force is not 0, it's 180. And the cosine of 180 is -1. So among all the other things we're going to write down, work is now negative. The field is doing negative work, slowing down that particle. Right? When it did positive work, the particle sped up because it was falling toward the negative plate. All right, so what's it moving? Is it moving from positive to negative, or is it moving from negative toward positive? Well, the charge is moving from negative toward the positive plate. And is it gaining potential energy or losing? Well, it's gaining because it's moving closer to the positive. It wants to fall down to here. And if you go farther away, it's just like throwing a ball higher up into the air. It's higher up, farther from where it wants to fall. When this particle goes over to the left, there's more distance for it to fall back to. All right, so then it gains electric potential energy is the type of energy it's gaining. And finally, it's kind of, I like to think of this as sort of like an uphill battle. We're fighting against the field. It's not falling freely the same way. It's kind of going opposite where it wants to go. Now, these are really important principles, and on our next quiz, this is a major part of what we're going to be quizzed on. Time for some really important equations. You see how we lose PE? Delta PE is negative when the work by the field is positive. And you see how we gain PE, so the delta, we would be adding positive amount. We're gaining when the work is negative. They're always opposite in sign. In fact, the relationship is far deeper. A deep principle in physics is that the change in PE is simply negative the work done by the field. So this is a huge part of so many things. We can derive the equation mgh from this principle. We can derive the equation 1/2 kx squared. I mean, after all, mg, that's the force. H, that's the distance, right? Force times distance is work. So there's a really, really deep principle at work here. At work. At work. Okay. And in physics, remember how we have some funny quantities, like electric field strength and potential difference? Here's how I like to think of that. If you walk into a room, there's a bunch of space in the room, and we can model that space with dots. So here you are, you walk in, and you say, I want to know what the temperature is. And you choose this point right in the middle. So you bring your thermometer there, and you measure the temperature at that point. Easy enough, right? Then you walk in a little later and you say, well, hey, I wonder what the strength is of the electric field right there in the middle. So you get your thermometer. No, not a thermometer. You get a small positive test charge. That's your thermometer. Maybe it has 3 coulombs. And you measure the electric force. And perhaps it's, 15 newtons. Now, you might be tempted to say, the strength of the field is 15 newtons, but that's not good enough. Here's the reason why. If you walk away and you come back later with a bigger test charge, right? So now your test charge is 4 coulombs big. You will feel a bigger force, and you might get confused. Whoops. You would feel a force of 20. And you might get confused. Which force is the correct force? Well, they're both right. What we do is we take that 3 coulombs and we imagine here's the charge zoomed in. Those are the 3 chunks, the 3 coulombs. Here's 1 coulomb. Here's another. I'm just kind of breaking it up into chunks. Chunk. And what would the total force be? 15. But how much force does each chunk feel? Well, 5 newtons. We're dividing up the total force across how many coulombs there are. And we say it's not 5 newtons, it's 5 newtons per 1 coulomb. That value is the electric field strength. It's just the force, right? But it's the force, not the total force. It's the force per 1 coulomb, okay? And in the exact same way, just how we take force and we divide it per coulomb, we distribute it across the number of coulombs in our test charge, we do the same thing for work and change in potential energy. This equation up here in blue, we are going to do the same thing. We're going to say the potential difference is the change in potential energy per coulomb. So if you let the charge fall, just like I showed before, you know, if you let the charge go from here at the beginning of the red arrow, where is it? There's the charge, and you move it over to here, there's distance in red. Oops. Distance. There's force in green. So work was done. How much work was done? Well, we don't care about the total work, right? Maybe the 2 coulomb charge, maybe it took 24 joules, right? To move the charge from here over to there. But we don't care about the total work. It would be negative, wouldn't it? And by the way, if it took negative 24, the charge will have gained 24 joules of potential energy. But we don't care about the totals. What was the energy gained per each 1 coulomb? If you cut this thing in half, how much energy did each coulomb gain? That's what potential difference tells you. And the answer would be, by the way, 24 over 2 is 12 joules per coulomb, or 12 volts, as we call it. So that's our definition for potential difference. And the second definition we have is the work done per coulomb. The work done per unit charge as a small positive test charge moves between 2 points. We don't really put the negative sign in the verbal definition. So there are 2 ways to define it. Here they are, officially, formally, if you want to write them down. This is it. There we are. And you can ignore the symbols if you want. I'm just showing that, you know, potential difference, that's the V, per, that's the division symbol, and so forth. So in lightning mode, here is a problem. We're given the picture here. Maybe we have to draw the field lines, but they always point from positive to negative. We know the strength of the field. That's the value of E. We know the distance traveled, although we want it in meters, so 0.18. And we know the charge Q. Okay, find the force. Oh, this isn't bad. Electric field strength is defined as the force per unit charge. So you need to plug in the E value in newtons per coulomb. The force is the unknown, and there's 3 coulombs. Cross multiplying gives 72. Next, we find the work from FD cos theta. Now, you always plug in the magnitude of force and distance. So the force is 72 newtons. The distance is 0.18 when we convert to meters. But what's the angle between force and distance? Well, positive charges feel a force in the direction of the field lines. So the green and red arrows have an angle between them of 0. There is no angle. Calculating that gives positive 12.96 joules is the unit. The change in potential energy is easy. It's just negative the work. They are negatives opposites of each other. So that's negative 12.96. To find the potential difference, V, we take, well, you can do either one. I'll just do delta PE per coulomb. So negative 12.96 joules per 3 coulombs. And this comes to 4.32 negative joules per coulomb, or volts.